Yes, so in this question, we have a question on control volume systems, one on mixing chamber and the other one on diffuser. Okay, we are told that determine the velocity at the exit of a diffuser. Okay, when carbon dioxide at 105 kilopascal and 300 Kelvin enters it with a velocity of 380 meters per second. And the exit state is 225 kilopascal and 370 Kelvin with specific heat loss. So here there is heat loss to the surrounding, which needs to be accounted for. Okay, so let us draw the diagram for the diffuser. Okay, so we have so we have the carbon dioxide enters at this state, and then it leaves. So this is state 1, and then we have state 2 at this state. Okay, and we have heat loss to the surrounding, Q out, which is equals to 5 kilogram. This is specific kilogram per, 5 kilojoules, 5 kilojoules per kilogram. Yes, so 5 kilojoules per kilogram. Now, we are told that inlet pressure P1 equals to 105 kilopascal, and inlet temperature T1 equals to 300 Kelvin, and velocity at the inlet V1 equals to 380 meters per second. All right. Then at the exit, T2 is given 370 Kelvin, and similarly P2 is also 225 kilopascal. Okay, so now the specific heat capacity for the carbon dioxide is also given. The CP for carbon dioxide is also given. It is 0.846 kilojoules per kilogram per Kelvin. Now we want to determine the velocity at the exit. So that is V2. V2 is not known. Oh, sorry, it's not a volume. This is volume flow rate. So we are talking about velocity. So what I wrote was volume. So this should be velocity, not volume flow rate. Sorry for that. Okay, so V1 and V2. So velocity V1 and then velocity V2. It's not known. All right. So if we look into the general equation, okay, from energy balance, for a control volume system, the total amount of energy in, okay, should be or minus the total amount of energy at the outlet should be equal to the change in the energy of the system. Change in the energy of the system. Okay? So, but at steady state condition, this is equals to 0. at steady state condition. So eventually we will have E in should be equal to what? E out. If you look into this system, there is some amount of energy of the flowing fluid. Let's say this is E1. And the energy flowing out is E2, energy of the flowing fluid. Okay, but you have to recognize that over here also we have the heat loss to the surrounding. So we need to account for it. Okay, so there are so many ways of solving this question. One important thing we should know is that the energy of a flowing fluid, okay, when a fluid is flowing into a controlled volume system, so energy of flowing fluid can be expressed in terms of E equals to mass flow rate of that fluid times the enthalpy plus kinetic energy of the fluid plus potential energy of that fluid. Okay, so this is very, very, very important. Okay, so from the fundamental equation governing the energy of a flowing fluid. Okay, so that if we look into this equation, let's see. So the total energy that is entering our system, one of them is E1, and the energy going out is E2, and we have Q out as well. So that if we consider this equation, the total amount of energy that is coming in is E1 should be equal to E out, that is E2. I'm sorry. So I'll say E2 instead. I'll say E2. So this is E2. Now, plus the heat loss. If you don't account for the heat loss, then the whole thing is zero because Q is coming out and we have Q out. All right. But in our question, the Q that is given, the Q out is expressed in specific quantity. And Q out in specific quantity can be expressed in terms of Q out, okay, Q out divided by mass flow rate. Okay, so that over here it means our Q out equals to specific quantity Q out times mass flow rate of the fluid, that's the carbon dioxide. So now we know the energy of the flowing fluid for this inlet. This is given by M1, okay, into bracket H1 plus kinetic energy at the inlet plus potential energy at the inlet, okay, and then this should be equal to M2 H2 plus kinetic energy plus potential energy, and then plus Q out times what? M. Now, at steady state condition, M1 equals to M2 equals to M. You understand me? So it means all these m's will cancel out, m will cancel out, and change in potential, change in kinetic energy, change in kinetic energy equals to 0, and change in potential energy is also equal to 0. You understand me? So all these terms will be cancelled out. So eventually we'll be left with what? H1 equals to, oh, I'm very sorry. So the velocities, I'm very sorry, and the velocities are known. So it's only the potential energy terms which will be equal to 0. I'm very sorry. Okay, so the kinetic energy terms is not equal to 0. I'm very sorry for this again. So because the velocities are given, okay, velocities are given, and we need to find the velocity at the exit. It's only the potential energy, sorry, the kinetic energy terms that are equal to 0. So this is not equal to 0. Be very careful, okay? So we have plus kinetic energy, okay? This should be equal to Q out plus H2 plus kinetic energy at the exit. Okay, so now let's see, one by one, H1 equals to what? You see, carbon dioxide is an ideal gas. So that for all ideal gases, H1 equals to Cp times T1. Because for any ideal gas, okay, the enthalpy of an ideal gas is always proportional to the temperature. So if you remove the proportionality sign, then we will have H equals to, we will replace the proportionality sign by Cp times temperature. Okay, so it means if I want to find H1 equals to Cp times the temperature. Be very careful. If the working fluid were to be water, okay, or refrigerant, then it does not apply to this case. Okay, so that H1 over here equals to, the specific heat capacity for carbon dioxide is 0.846, okay, times the temperature. Temperature T1 is 300 Kelvin. So this gives me, if you solve carefully, 253.8 kilojoules per kilogram. You understand? So now the kinetic energy, KE1, also kinetic energy E1 equals to the velocity square divided by 2000. Okay? So divided by 2000. Okay, so normally it is supposed to be KE equals to the velocity square divided by 2. Okay, that's the formula for kinetic energy. But this is in meters square per second square. So before we can convert, we need to convert into this unit. If you convert into kilojoules per kilogram, then you need to divide by 1000. So that's why we multiply this by 1000. So this now becomes kilojoules per kilogram. You understand me? If you don't divide by 1000, then the unit is going to be meters square per second, which does not conform with this unit. You understand me? So all the units has to be the same. Okay? So now we will have a situation like this. We know the velocity at state 1. Okay, so this gives me 380, okay, square divided by 200. Sorry, 2000. All right. So if you calculate this carefully, okay, this gives you about 72.2 kilojoules per kilogram. All right. Then same thing, if we have to find H2, H2 equals to Cp times T2, which gives me 0.846 times 370. And this gives me 313.02 kilojoules per kilogram. All right. So now we don't know the kinetic energy, we don't know the velocity at state 2. So that's what we are interested in determining. So now we know H1, we know H2, we know Ke. So in this final equation, okay, so we can find Ke2. So Ke2, kinetic energy at state 2, equals to H1 plus kinetic energy state 1, okay, minus Q out minus H2. Okay, so this gives us we will have 253.8 plus 72.2 minus 5 minus 313.02. So the kinetic energy at the exit is 7.98 kilojoules per kilogram. Okay, so kilojoules per kilogram. Now, we need to determine the velocity at state 2. All right, so the kinetic energy at state 2 equals to V2 square divided by 2000. V2 square divided by 2000. So it means that V2 square equals to kinetic energy at state 2 times 2000. All right. So that my V2 equals to, if you take the square root of both sides, then we will have V2 equals to 126.33 meters per second. Okay, so this gives us the velocity at the exit. Okay, now the next question says, consider an ideal adiabatic mixer. Okay, so consider an ideal adiabatic mixing chamber with 2 inlets and 1 outlet. Okay, cold water at 12 bar and 25 degrees Celsius enters the inlet number 1, and superheated steam at 12 bar and 250 degrees Celsius enters the inlet number 2. Now, if the mixture leaves the mixing chamber outlet at 12 bar, okay, so with moisture content of 25%, determine the ratio of the mass flow rate of the cold water and superheated steam, neglecting the effect of pressure loss. Okay, so let us reflect in this question. Okay, so we want to determine the ratio of the mass flow rate. So first, let us draw the mixing chamber. So a mixing chamber can be of this form. Okay. So this is inlet number 1. Inlet number 2 is this. So number 1, number 2, and this is the exit, number 3. So the temperature over here is 25 degrees Celsius, equals to T1. And T2 equals to 250 degrees Celsius, T2. And the pressure, operating pressure equals to 1200 kilopascal. All right. So, and the moisture content, okay, at state 3, that is X equals to X3 equals to 25%. So X3 can give us 0.25. All right. Now we need to establish the energy balance throughout the system first. Okay, first thing is that we want to find, says determine the ratio of Y, the ratio Y of the mass flow rate of the cold water and the mass flow rate of the steam. Okay, so means that we want to, if the mass flow rate of the cold water, let's say this is M1 and this is M2, and this will give us M3. Okay, so we want to find the ratio of the mass flow rate of M1 divided by M2. So it means Y equals to M1 divided by M2. That's what we are interested in. Okay, so it means we need to find the mass flow rate M1 and M2. First, we need to write down the equation, energy balance, energy balance. From this energy balance, I'm told that the total amount of energy inlet should be equal to the total amount of energy at the exit. Okay? Here, since the fluids do not have any velocities, so it means the kinetic energy terms, potential energy terms are negligible. So again, if we allow the energy of the fluid so if we say that E1, the energy of the fluid here is E1, and the energy of the flowing fluid over here is E2, and similarly over here we have E3. Okay, so the total energy going in, this gives me E1 plus E2 could be equal to E3. So what is E1? E1 is mass flow rate, M1, H1 plus kinetic energy, E1 plus potential energy, P1 plus M2, okay, H2 plus potential energy, P2 plus kinetic energy, Ke2. Okay, and then this must be equal to M3, and then H3 plus kinetic energy K3 plus potential energy P3. Now, one thing you should know, the change in potential and kinetic, the assumption, basic assumption is that change in potential and kinetic energy terms will be equal to 0 because no velocity is given. No velocity is given. All this will be equal to 0. All this will be equal to 0. So now the equation reduces to what? We will have M1 H1 plus M2 H2 equals to M3 H3. Okay? So now, from the mass balance, M1 plus M2 equals to what? M3. Okay, so now we can make some manipulations here and there. Okay, some substitutions as well. Okay, so we know that given that y equals to M1 divided by M2. Okay, so we can express let's divide this equation by M2. Divide this equation by M2. Divide by M2. See, so that gives us M1 divided by M2, okay, times H1 plus M2 divided by M2 times H2 equals to M3 divided by M2 times what? H3. M1, M2 will cancel over here. So then we will have, but M1 divided by M2 is Y. So we will have Y over here. Equation becomes Y times H1 plus H2 equals to, again, we will have let me see over here. Okay, so that gives us M2 divided by M3. Yes, so we have M2 divided by M3. Okay, so now we will have from this, so we have, let's see over here. 1 minute. Yes, so we know that by definition, M3 equals to M1 plus M2. So I'll substitute into this equation. So let's cancel this first out. Okay, so let's see, rewrite this equation like this. So this gives me H1 Y times H1 plus H2 equals to M1 plus M2 divided by M2 times what? H3. So now this gives me, if I divide through split, so it gives me YH1 plus H2 equals to M1 divided by M2, that gives me Y times H3 plus, again, M2 divided by M2. So that gives me H3. So therefore, I'll have Y, if I rearrange this equation, Y now becomes equals to H3 minus H2, all divided by H1 minus H3. Okay? So that's it. So now we need to find the enthalpies at state 1, state 2, state 3. So that's our job now. So now the properties of the fluid at state 1. At state 1, we know that P1 equals to 1,200 kilopascal. And similarly, T1 is equal to 25 degrees Celsius. So now we need to determine this state. Is it superheated? Is it compressed liquid? Is it saturated liquid vapor mixture? First, we need to find T saturation at what? 1,200 kilopascal. So if you determine this from property table, this gives us 187.96 degrees Celsius. So what is your conclusion then? So we discovered that T1 is less than T saturation. So can somebody guess what will be the fluid, state of the fluid? So T1 is less than T saturation. So it means, so if we draw on our TS diagram, this is T saturation is this. This is T saturation. So now it means T saturation is greater than T1. So T1 will be somewhere here. You understand me? So if that is the case, then we need to conclude that state 1 is in the compressed liquid state. You understand me? So now, so therefore, state 1 is compressed liquid. If it is compressed liquid, then we need to go to the compressed liquid table to look for the properties. But I've told you, if you go to the property table, okay, at the compressed liquid state, at this pressure and temperature, you will not find the properties of the fluid or the enthalpy. So we will make assumption. I think I've discussed this in class with you some time ago, at the immediately beginning of the semester. So then we conclude over here that the enthalpy H1 is equal to HF at the given temperature, not pressure. Okay, so then this gives me 104.83 kilojoules per kilogram. Okay, so now that is it for state 1. Now we need to move on to state 2. Now at state 2, we have At state 2, what do we have? The properties. P2 equals to 1,200. Be careful over here. The operating pressure is the same. You see, the pressure which is given is common to all the states. State 1, state 2, state 3, the pressure is the same everywhere. So that's a uniform pressure. Okay. So now we need to determine. So T2 is 250 degrees Celsius. So using these two properties, we have to find H2. How do we determine H2? First, we need to identify the state of the fluid. So then it means we need to find T saturation. So if you T saturation at 1,200 kilopascal equals to 187.96 degrees Celsius. So now what is your conclusion now? Superheated, because T2 is greater than T saturation, implies superheated fluid. So now we will go to the superheated table. Under superheated table, H2. So from table A6, okay. So then H2 equals to 2,935. Sorry. So we have 2,935.6 kilojoules per kilogram. Okay, so that is it for the enthalpy at state 2. Now we need to determine the enthalpy at state 3. Now at state 3, what is the condition? At state 3, okay, at state 3 we are told that X, that is the vapor fraction, equals to 0.x3 equals to 0.25. Okay, so this implies that state 3 is what? State 3 is saturated what? Liquid vapor mixture. You understand? Okay, so therefore H3 will be equal to HF plus X HFG, okay, all at 1,200 kilopascal. So now HF from the property table, this gives you 798, okay, 0.33 plus 0.75 times 1985.4. Okay. So eventually this gives me H3 equals to 2287 0.38 kilojoules per kilogram. Okay, so now we can determine our Y, value for Y. So therefore Y equals to H3 minus H2 divided by, so divided by, let's see, so H1 minus H3, okay? And then, so this gives me 2287.38 minus 2935.6, all divided by, okay, so we have all divided by 104.83 minus 2287.38. Okay, so now Y gives me 0.297. Okay, so that's the end of this question. So is there any question from anybody? Okay, before we proceed.
No, sir.
Okay, so then I'll proceed to the next question. Yes, so this is another question. December 2016. Okay, so it is a test question. December 2016. It's a test question. It says that question number 1, by means of a diagram or by means of diagrams and appropriate coefficient of performance equations, explain the difference between refrigerator and heat pump. Okay, so a refrigerator, they have something in common, a refrigerator and a heat pump. Okay, so a refrigerator normally is given by this refrigerator, and then we have, let's say, heat pump right here. So a refrigerator, what it does is that it takes heat from the refrigeration compartment and by means of some pumps, which is W in. Okay, so we have the refrigerator space. This is refrigerated space. So from this refrigerator space, some amount of heat, namely QL, is taken by means of this W in. Without a W in, the refrigerator will not be able to work. It's just like if you go to Giant, you buy a refrigerator, you don't plug it to the socket, it will never work. So then this is QH. All right. So then for a heat pump, yes. So what is the COP? The COP for a refrigerator equals to what? The desired output. Desired output is QL divided by the required input, which is W in. Okay. And similarly, for a heat pump, okay, let's say you have a house over here, which is very cold in winter. Okay, so they install a heat pump. So the heat pump, what it does is that it takes heat from the surrounding. Heat is taken from the surrounding, and the heat is rejected. So the magnitude of the heat is QL, and this heat is rejected to the room where the heat is needed. So that for a heat pump, the desired output is the QH. Okay, so coefficient of performance for a heat pump equals to QH divided by W. Okay, so that's the answer to that question. And then the next question also states that an engine working on an Otto cycle with a cylinder bore of 50 mm and stroke of 90 mm and clearance volume of 25, calculate the compression ratio and thermal efficiency of the cycle. Okay, so I have discussed this question before with you. Okay, if you remember very well that if you have a cylinder like this, okay, so we have the V minimum over here, and we have the V maximum over here. That's the maximum volume. Okay, so this corresponds to V1, and this corresponds to V2. And the bore of the cylinder is the diameter. That's the bore, diameter. And then the distance between the top dead center and bottom dead center is given by L. And the volume occupied by this is called VD. That's the displacement volume. Okay, so now sometimes it is called the swept volume. Sometimes it is called VS, where VS is called swept volume. Swept volume. Okay, so now they say we should find the compression ratio, R. So what is R? R equals to V max divided by V minimum, which is equal to V1 divided by V2. Okay, so we have to move a bit faster. Maybe this will be the last question I'll solve for today, and then we will make to the next week. Okay, so we have V2, the parameters that are given, the diameter is given equals to 50 times, I will convert directly, so it is 50 mm. So this equals to 50 times 10 raised to the power 3 meters. And the stroke, okay, so stroke L equals to 80 mm, which is equal to 80 times 10 raised to the power minus 3, okay, m meters. So now the minimum volume, V minimum, equals to VC. That's the clearance volume. Okay, so this is the same as VC. This is called clearance what? Volume. Clearance volume. Okay, so now this clearance volume is given in the question. It's 25. Oh, I think it's the same thing I solved last time. It's just a repetition. Okay, so this equals to 25 10 raised to the power minus 6 meter cube. Okay, so now let's see. Now we have to determine, we have to know that the value for okay. So the value for R equals to V maximum divided by V minimum. Okay, so V minimum is given by the clearance volume. Okay, so V minimum equals to VC, which equals to 25 10 raised to the power minus 6 meter cube. And V maximum, V max equals to V minimum, VC plus VD or V displacement volume. Let me show you. So this volume. Okay, so Vs, okay, so V maximum, this V maximum should be equal to the whole of this volume plus this volume. Okay, so V maximum, sorry, V max equals to Vs or Vd plus Vc. Okay. Okay, so now we will have Vc plus Vd. Okay, so now this gives me, but how do we determine Vd equals to pi d squared divided by 4 times L. So now this gives me pi 0.05 okay, raised to the power 2 times 0.09 all divided by, that's the diameter, divided by 4. Okay, so Vd equals to 1.76715 times 10 raised to the power minus 4 meter cube. Okay, so now our V maximum equals to 1.76715 10 raised to the power minus 4, okay, plus 25 times 10 raised to the power minus 6. So this gives me 2.01715. times 10 raised to the power minus 4 meter cube. Okay, so finally, the value for R give me R equals to 2.017 times 10 raised to the power minus 4 divided by 25 times 10 raised to the power minus 6. And this gives me 8.069. Okay? So therefore, thermal efficiency equals to 1 minus 1 over R K minus 1. And this equals to 1 minus 1 over 8.069 raised to the power 1.4 minus 1. So this equals to 0.566, which is equal to 56.6%. Okay, so that's the efficiency of the cycle. Okay, so I think it's already 5:30. So I'll stop over here. For the the subsequent question, I will send to you. I'll send a solution to you for you to check. Okay, so inshallah we'll meet again on our next meeting will be next week Monday. So next week, inshallah, I'll start with chapter 6, and then we'll be solving some questions alongside. Okay, so is there any question so far from any of you?
No, sir.
All right, so let us, I'm coming in 1 minute.